If you have any questions about localytics, Clay is your guy. He's right over there. He's waving. DataCamp's going to be filming this, so Nick's your guide for DataCamp. They're a platform for learning data science in your browser. So we're lucky to have Alex today, who is about to defend his thesis in 2 weeks, so we're incredibly lucky to have him today. And he works in the statistics department at Harvard, but has done a lot of work in sports analytics, especially basketball analytics. So he's part of a group that does a lot of work using player tracking data, so like the XY coordinates of where the player is on the floor, and take it away.
Awesome. Hey, thank you all for having me. This is going to be a sort of package level talk. If any of you want any sort of more nitty-gritty details afterward, we can certainly talk about those. And yeah, this work is done jointly with a group. We call ourselves XY Research. We're a bunch of people who were at least at one point affiliated with Harvard. And I'll show you guys a slide of these folks in a second. All right. So when I present sports work, there's like two groups of people who respond to that. The first group of people say, of course you're talking about sports, that's great. Why are you studying math and statistics? There's another group of people who are like, math and statistics is awesome, but why are you wasting your life on sports? So I'll answer the more fun question, why sports? Actually, these two things have been very interrelated for me. When I was an undergrad, I was a terrible statistics student, but my roommate read Moneyball our sophomore year, and then discovered in Moneyball that there was a professor at Harvard that he wanted to talk to, named Carl Morris, who's a pretty big deal in statistics. And then from there, he ended up roping Carl into starting an undergraduate sports analysis club. In that club, I ended up working with Carl on a paper for estimating baseball park factors. So how different baseball ballparks are sort of more favorable for hitters or pitchers depending on their shape. You know, for example, Fenway Park is this giant wall that makes it very easy for hitters who hit to that side of the field to hit a ball off the wall and get a double. So we ended up working on a project there, and then I realized that I actually really liked statistics, but by that point had already committed to a job at Lehman Brothers in 2008. But luckily I already had the light bulb, so managed to sort of get right back on the academic track earlier than expected. Yeah, but on a less personal note, sports I think is a great laboratory for learning about statistics. So for example, this is a figure from a 1977 Scientific American article that Carl, depicted on the previous slide, wrote with Brad Efron, another big statistician over at Stanford. And this actually is about estimating a player's batting average, just starting from the first, I think it was the first 10, 20 games of the season, and trying to estimate what their batting average is going to be at the end of the season, right? So I think most people here are familiar with this fundamental idea of regression to the mean, and the basic idea here was that at the very beginning of the season, you're going to see some hitters who have really unrealistically high batting averages. You'll also see some hitters who have unrealistically low batting averages. And if you want to have a good estimate of what their true batting average is going to be over the entire season, you actually need to sort of pull these estimates together. And so this is an idea in statistics and machine learning that's now very popular called shrinkage, where you want to shrink a bunch of these estimates together so that they're actually reasonable. It's a form of regularization that's also data-driven. And it's great that a fundamental example that came from one of these major developments in statistics was actually phrased in terms of baseball. Of course, a lot of people also know shrinkage in Seinfeld. All right. So if we fast forward a little ways, I went from being a B- student in statistics to being in a statistics PhD program. There I met a group of great people who were also working on sports data. One person, if you're a real sports nut, you might know is Kirk Goldsberry. He was a columnist for Grantland while it was still around, and now actually works for the San Antonio Spurs. It was also 3 other students, 2 statistics grad students, Dan Cervone and Alex Franks, who are now postdocs at NYU and University of Washington, respectively, and Andy Miller, who's still in the CS department at Harvard, and a statistics professor, Luke Bourne, who's now at Simon Fraser University. So Kirk was able, through his connections and through being an analytical voice in the basketball community for some time, he was able to get very early access to this player tracking data that they have now installed in all the arenas in the NBA. And so from there, he recruited Luke, whose specialty was in spatial statistics, and then they recruited a group of grad students to start working on some basketball problems. And so the work that I'm going to show you today has come out of this collaboration, which is now a multi-site collaboration, but at one point was a Boston collaboration. The work here that I'm presenting has been presented at the Sloan Sports Analytics Conference several times. And so if you also follow that community, some of this might be stuff you've seen before. All right. So what is the big deal about this player tracking data? In every NBA arena now, starting from the 2013-2014 NBA season, they installed these modified security cameras in the rafters of every NBA arena. And so there are, I think, 6 cameras that are tracking the players as they run around on the floor. And what this gives us is a 24 frame per second track of all 10 players. They used to have the reps, they took the reps out. And XYZ coordinates of the ball. So there's a whole lot of data there, and what it gives you is this, whoops, come on here. It gives you this very cool sort of high resolution picture of what's going on in a basketball game. So this is what we end up being able to work with. So it is XY coordinates. There's some information that we're missing, right? These dots don't have arms. We can't see which way a player is facing. But there's still a lot of very good information that's here. And a lot of the work that we've been doing is to extract some signal here and get some actionable intelligence that teams or players might be interested in. Great. So I don't know if this thing skipped ahead and gave this away. I think I'm touching this. Anyway. This is one thing that the player tracking data actually gives us a lot of insight into. Right, we want to, well, in basketball statistics, we've been able to collect a bunch of statistics, right? If you think about it, the game is basically just right, there's the famous XKCD comic, right, that this is just a weighted random number generator that we tell stories about. So a game is already generating statistics, whether it's scoring, the number of fouls, the number of rebounds, etc. But the spatial aspect of the game is something that we obviously know is critical from watching the game. So how can we start incorporating the spatial aspect into the way that we analyze the game? And so the importance of the spatial aspect is something that you can see very clearly. If you think about aggregating statistics, just integrating out all the spatial information, you can actually end up misleading yourself very much, even if you think that you're doing something that's very data-driven. So this is one great example that just came up in our group this week. The question is, does the distance of a challenging defender matter when a shot is being taken? And so if you plot the log odds of somebody making a shot, conditional on the defender distance from 0 to 8 feet away from the players, right? What you would expect is for this probability to be going up. But if you just look at all the shots that happen in the NBA, right, very large sample size that we have here, you see that the line actually looks pretty flat. So does anyone have an idea of what's going on here?
Is it the defender closest to the shooter that you're measuring?
Yes, it is the defender closest to the shooter.
The defenders are closer when the player is closer to the basket.
Yeah, that's exactly it, right? So there are these, like, whenever we're dealing with a system where there's something very complex going on, and we perform an aggregation where we're aggregating over different states, some of which are more common, some of which are less common, it's very probable that something like the Simpsons paradox is going to come up, right? Where the correlations at the aggregated level are very different from the correlations at the much more specific level. So here you can see that if you actually break down the shots by how close they are to the basket, right, that defender distance actually has a huge effect on the probability the shot is going to go in. Right? So this line up here shows dunks. Right? So if somebody is 8 feet away from you and you're dunking the ball, you're probably on a fast break. Right? Or if the nearest person to you is 8 feet away. And down here you have different long-range twos and different three-point shots. Right? The size of the dot here is how common each of these situations is. So when you're dunking the ball, it's very common that the nearest defender is 1 foot away from you. Right? But if you're taking a three-point shot, it's very common that the nearest defender is 5 feet to 8 feet away from you. Right? So because of the way that, in three-point shots, a far-away defender is more common, but in close-up shots, a nearby defender is more common. When you actually perform this averaging, you end up with a flat line. So this is just one clear example of how having data that's at the resolution at which you want to be making decisions is incredibly important to make sure that that data is actually steering you in the right direction. Right? If you aggregate your data the wrong way, you can end up fooling yourself and thinking that something that is untrue is actually true. I thought this was a great example of how spatial context matters. And it's not just for answering new questions, it's for answering old questions. Okay, so working with this new data set, there are a bunch of new challenges that come up. There are also a bunch of great tools that we have to deal with this. On one hand, right, we're dealing with a very complex process. We're trying to understand the entire game of basketball. We're not trying to we're trying to, make to understand aspects of basketball that will have real impact, right? So we're not trying to look at a very small corner of basketball. We're trying to answer some fundamental questions there. And that means that we really have to understand this game that has these discrete events, for example, shots or passes happening in continuous time, and where there are a lot of heterogeneous agents that are actually engaging in this process, right? That are creating this process. And so to deal with that kind of process, the sort of modeling tools that we're using are spatial process models. These are ones that describe how discrete events happen in a spatiotemporal support. Temporal evolution models that describe how a system evolves in time. So you can think about like hidden Markov models, time series models, being examples of those. We also need random effect models, or models that are able to estimate individual effects in a way that doesn't end up overfitting. Right? So we need some sort of regularized estimation of individual effects. And because this is such a complex system, there's not going to be a single method or model that we're going to be able to use to or a single algorithm that we can throw at this to answer all of our questions. And so thinking about how to compose different models, thinking about how to factor the problem into pieces that are actually tractable so that we can feed them into each other is a major part of how we think about modeling this process. Now on the other side, right, when we think about what we're trying to get out of these models, right, the queries that we are demanding of these models that we're fitting are actually also very complex, right? We want personalized inferences. We don't want to say, we don't want to recommend to a GM that they should go out and trade for the league average player who doesn't exist, right? We want to say that you should go and trade for this particular player, right? You should go and try to get Kevin Durant. I'm headed to Berkeley, so I'm speaking. Right. You also want to be able to say something about how teams are going to perform even after the context changes, right? So, for example, if we want to understand how Oklahoma City is going to play next year, besides weeping horribly, we're going to have to perform some kind of extrapolation. We have to understand how the different components that are part of that team are going to be playing basketball in a situation that's very different from what we've been able to observe before. And then finally, right, if we're actually using these models to do something like player evaluation, we would like to be able to point to what we think changed the value of a given moment in a game, right? We'd like to be able to attribute changes in our estimates to something that actually happened, to some new information. And so these actually form a set of very interesting requirements that sort of inform what tools we're going to end up using. So in order to do personalized inferences, we're going to use priors that share information in ways that, that reflect the similarities between different players. And we try to use data to inform how we determine that one player is similar to another. We have to do some form of dimension reduction or representation learning, right? If you think about it, if we just think about how a player behaves on the court, and we're trying to make a spatially referenced decision about what a player is going to do, we're already talking about an uncountably infinite space, right? Because like inches matter in basketball. So you have to actually be able to share information spatially in order to do that. And with all the inhomogeneities that there are on the court, really the only way to do that in an effective way is to find some nice representations of the space in a sort of reduced dimension form. If you think about the actions that the players are performing, you want to be able to represent those actions very, very parsimoniously. And so representation learning is also very important. In order to extrapolate, we need to think about how to factorize the problem in a way where we can take a profile for a given player and stick it into a new lineup and have that actually predict fairly well how that lineup is going to perform. That's still a really hard problem that we are not near solving. And then finally, in order to be able to make attributions, right, we need to have, we need to be making predictions that not only repredict very well the things that we observed, but also that predict counterfactuals very well. So this is something that's very important for thinking about strategy, and also for making sure that if you try to, well, this is actually something that I'll talk about in the next application in a little bit less abstractly. So this is an overview. I'm just trying to give you a sense of the many different tools that we're using here, right? This is not the kind of problem that fits very neatly into like a regression or a classification setting. So it's something that does require a lot of tools that aren't necessarily in the sort of standard machine learning toolkit.
Did you add other sources of data on top of this data from the players?
Not a ton. Yeah, in fact, so the data that we ended up using were the player tracks. There were annotations of the events that happened in a game, so like this person passed to that person, and things like out of bounds, foul, that kind of thing. But you know, there were a lot of things that we didn't include. For example, player height and weight is available. That's something that can be very useful for looking at energy expenditure or something like that. So what we looked at was almost all self-contained in the tracking data itself. Great. Okay. Oops. Let's see here. This is. Well, let's watch some basketball first. So you can watch this a couple of times. We're very partial to the Spurs. We really like how they play basketball. This is from the 2013, 2014 season, I think. This was a buzzer beater. Cleveland was ahead by 2 points against San Antonio. There are 9 seconds left in the game. And Matt Bonner inbounds the ball to Tony Parker, who drives towards the basket. Tony Parker then notices that Kawhi Leonard is wide open in the corner 3. He passes the ball to Kawhi Leonard. He shoots it. Right. Now, when you're watching this possession unfold, depending on how much basketball you watch, you may get very excited long before Kawhi Leonard actually takes this open 3-point shot. Right? Because you sort of understand that as soon as there's a man who's open in the corner 3, who's a good 3-point shooter, then good things are probably going to happen. Right? And so we had this idea that there should actually be something like a stock taker for a basketball possession, right? Now that we have all this spatial information here, we should be able to encode that sort of gut feeling that you have as a fan, where you say, okay, I know exactly how well my team is doing right now. And so we want to be able to turn it into a curve that looks something like this, right? So when we start at the very beginning of that possession, the point value is close to the baseline, which is about a little bit less than 1 point. Then as Tony Parker drives to the basket, actually I have this sort of annotated here. So Tony Parker is now driving to the basket, going around the screen. He enters the restricted area, so he's much closer to the basket now. This is where he's got the basketball. And so the possession value has already gone up, right? Because it's very likely that he can take a shot from here. And it's actually a very high value shot if he decides to take it from that close to the basket. At this point, Tony Parker notices that Kawhi Leonard is open in the corner three, right? So he passes the ball to Kawhi Leonard, and suddenly there's this huge uptick in value, right? Even before the shot is taken, there's a large uptick in value. And then this entire region here is where Kawhi Leonard is actually gathering the ball and taking the shot. And the contest is too late, and at the moment that he shoots the ball, the expected value is something like 1.6. Right? So the general idea here is that just by moving around the floor, by making decisions that aren't necessarily terminal decisions, decisions that are going to end the possession, a lot of value is created and destroyed in a basketball play. And what we'd like to be able to do is to attribute that to actions that are actually occurring on the basketball court.
This accounts for the situation. 2-point extends the game, 3-point wins it.
This one doesn't. So this isn't a win probability. This is just possession value. So we're looking at just this individual possession. Although we did get into long discussions with people about this, and it turns out that that maximizing possession value in this case would probably also maximize your win value.
As Tony Parker is going close to the center, you should have like a decreasing expected value because he's missing the 3-point shooter. He exhibits less probability of actually giving it to the thing that is going to actually most likely close the deal.
So what we actually have going on here is that as Tony Parker is moving moment by moment, we're calculating the probability that Tony Parker is going to pass the ball off to the 3-point shooter versus take his own shot. And so, right, the fact that this isn't, right, that there appears to be a trade-off happening here, right, where like it's not going straight up in his proximity to the basket accounts for that trade-off. And that's a very good point and something that we'll actually talk about at the end of this.
I was wondering, actually if that shouldn't be going up sooner as soon as he got open.
Yeah, so that's another thing that, right, I think that there are a lot of different EPV curves that you can think about. So like if you live in the head of Greg Popovich, the Spurs coach, right, perhaps even at the moment that Tony Parker goes around that screen and you sort of see the positioning of the players, right, maybe that's when the EPV should actually be spiking. So the time at which the possession value spikes depends a lot on your representation of how the play is unfolding. What we used here was a very rudimentary, like very basic representation of the possession that basically just looks at the positions of the players, the open passing lanes. This is something I'll talk about in a second. Right, the most informed way to think about this is that basketball play is actually a sentence that has a bunch of words in it, right? And these are sort of actions that can be grouped together. So by the time an action starts, you already know where it's headed. And then that makes the basketball possession look more like a tree instead of looking like this sort of continuous time frame. Once you can break down a possession into a tree, then you can start seeing EPV spiking at much longer time ranges because, right, these motifs are actually tying together things that are separated in time that you know are going to occur that way.
Actually, I just want to confirm, is this a quantitative curve here, like there's some function? Okay. And
Yes.
why does the value go down between the time the shooter gets the ball and until he shoots it?
So that's actually because Dion Waiters here, who actually is responsible for most of the value in this play, because he was just sort of hanging out in over here instead of guarding Kawhi Leonard during this play. He notices once Kawhi Leonard gets the ball and starts running toward him far too late. Actually, what's really funny about this play is that in the previous play, Dion Waiters was the one who had put Cleveland up by 2, and so he was still sort of celebrating at this point, and thought that he'd won the game for his team, and decided not to play defense. Yeah, which is why Kawhi Leonard was there. But this here reflects that Dion Waiters is trying to close out the shot.
So in this expected possession value function, are you primarily looking at the position of the ball and how the ball moves, or do you ever account for like the distance between players of both teams
Absolutely.
to each other?
Yeah, and that's something that I think we should get into, because it's kind of cool. Okay. Yeah, these are figures from, we actually managed to get a basketball paper published in the Journal of the American Statistical Association, which like we're super proud of. But these are figures from that paper that show a different possession that has a little bit more meat to it. And yeah, so we're excited about that. Okay, so I think everyone sort of understands the expected possession value idea, that it's the number of points the offense is expected to score by the end of the current possession, given all the information that we have now, right? So the idea is that, right, the number of points the offense is expected to score is, like, if you sort of think fatalistically, right, that all uncertainty is just the fact that we don't have enough information to know exactly what's going to happen in the future, right? This is sort of a fixed event, right? The only thing that's changing over the course of the possession is how much information we have about that event. So if you think about that this way, then the sort of expected possession value curve is actually repredicting the same event over and over again, right, millisecond by millisecond. And so if you want to formalize that, right, we have, we're writing the full resolution annotated player track as Z. If you think about the history that's generated by that entire player track, we can write it as a filtration, the history of Z up to time t. Capital T is the time the possession ends. We don't know when that's going to be while we're watching the possession, right? So that's also a random variable. And then at the end of the possession, the analysis here simplified things. So we're only looking at 0, 2, or 3 points that are scored. So we're not looking at free throws. And right, what we can do is write the expected possession value as the conditional expectation, given everything that we know up until now, of the random variable x, right, the number of points that are scored at the end of the possession. If we write out all the uncertainty that we're integrating over, right, it's a double integral over one way to represent it is a double integral over the time at which the possession is going to end, and then the state at that time. Right? Really what this is an integral over all the paths that possession can take. So one thing, if you sort of work with machine learning in a practical context instead of working for several years on a single problem to get a paper published, you might ask, why are we doing something that is so complicated, right? If you look at this outcome here, right, there are 3 classes of outcomes. Why aren't we just using a standard machine learning classifier to figure out whether it's going to be 0, 2, or 3, given like the snapshot of the players at a given time? I think this is sort of an important point, that what we want to be able to do with this is to evaluate player decisions. Right? We want to be able to say that if the value changes between time t and time s, that's because of something that happened on the floor between time t and time s. Right? And so there are several examples where if you don't use a coherent estimator, right, one that is itself a martingale, so its expectation only changes if there's additional information that's added to it. Well, it's a special kind of martingale. Then you can end up in these sort of weird paradoxical situations. So one that I completely made up says, okay, let's say that we look at all the situations during a season where Tim Duncan, God rest his soul, is at the corner 3 at time t, right? This is a very rare event. He usually didn't have the ball at the corner 3. And we look at the next time point, right? The next person to possess the ball, right? So here we're looking at the, let me see here. Okay, yeah. So here we're looking at, in parentheses, the total number of possessions that you actually observe this occur, right? So in the 20 possessions that Tim Duncan had the ball at the corner 3, 10 of the times he passed it to Tony Parker in the restricted area. 10 of the times he passed it to Kawhi Leonard in the mid-range, right? And then in each of those 10 possessions, a total of 12 points and 10 points was scored. Right. So if we just look at this side of the table, it's summarizing all the times where we saw Tim Duncan in the corner 3, and it enumerates all of the downstream outcomes that happened after that. Right. Now what we can also do is look at all of the